Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be discussing air handling units. We'll be looking at some typical examples to understand how they work and where to find them. Just before we jump in, I want to say a quick thanks to Danfoss for sponsoring this video. Danfoss is committed to spreading engineering knowledge around the world by both partnering with channels like this one and also by offering free online classes through their online portal, Danfoss Learning. They have literally hundreds of lessons available on a wide variety of topics, including relevant classes for air handling units. You can also take exams and earn certifications to give your career and your confidence a boost. Just click the link in the video description below to create your free Danfoss Learning profile and gain access to a world of knowledge. Pop engineering quiz. What is the difference between an FAHU and an AHU? Let me know your answers in the comments section below. If you don't know, then give it your best shot. No cheating, just test yourself, and I'll give you the answer at the very end of this video. So where do we find air handling units? Air handling units, which usually have the acronym of AHU, are found in medium to large commercial and industrial buildings. They are usually located in the basement, on the roof, or on the floors of a building, and many large buildings will likely have a mixture of all of these. AHUs will serve a specified area or zone within a building, such as the east side or office areas from floors 1 to 10, or perhaps a single purpose such as just the building's toilets. Therefore, it's very common to find multiple AHUs around a building. Some buildings, particularly old high-rise buildings, will have just one large AHU, which is usually located on the roof. These will supply the entire building. They might not have a return duct. Some older designs rely on the air just simply leaking out of the building. But this design is not so common anymore in new buildings because it's very inefficient. Now it's most common to have multiple smaller AHUs supplying different zones to give better control and higher quality space conditioning. Buildings are now also much more airtight, so we need to have a return duct to regulate the pressure inside the building. So what is the purpose of an air handling unit? Air handling units condition and distribute air within a building. They take fresh ambient air from outside, they then clean this, heat it or cool it, maybe humidify or dehumidify it, and then they'll force it through some ductwork around to the designated areas within the building. Most units will have an additional duct run to then pull this dirty used air out from the rooms back to the AHU, where a fan will discharge this back into the atmosphere. Some of this return air might be recirculated back into the fresh air supply to save energy. We'll have a look at that later in this video. Otherwise, where that isn't possible, thermal energy can be extracted and fed into the fresh air supply intake to also save energy. Again, we'll look at that in much more detail later in this video. Let's have a look at a simple, typical AHU design, and then we'll look at some more advanced ones. In this very basic model, we have two AHU housings for flow and return air. At the very front, on the inlet and the outlet of each housing, we have a grille to prevent objects and wildlife from entering into the mechanical components inside the AHU. Here's a photo of an AHU intake that would have sucked in a whole bunch of trash if the grille wasn't there, so that's why it's important to have this installed. At the inlet of the fresh air housing and the discharge of the return air housing, we have some dampers. The dampers are multiple sheets of metal which can rotate. They can close to prevent air from entering or exiting the AHU. They can open fully to fully allow air in or out, and they can also vary their position somewhere in between to restrict the amount of air which can enter or exit. I'll also show you some examples here of real-world dampers in AHUs. The one on the left has the motorized controller visible, which changes the position of the dampers. After the dampers, we'll have some filters. These are there to try and catch all the dirt and the dust, etc. from entering the AHU and also the building. If we don't have these filters, the dust is going to build up inside the ductwork and within the mechanical equipment. It's also going to enter the building and be breathed in by the occupants, as well as make the building dirty. So we want to remove as much of this as possible. Across each of the filter banks, we'll have a pressure sensor. This will measure how dirty the filters are and warn the engineers when it's time to replace the filters. As the filters pick up dirt, the amount of air that can flow through them is restricted, and this causes a pressure drop. Typically, we'll have some panel filters or pre-filters to catch the largest dust particles. Then we'll have some bag filters to catch the smaller dust particles. We've actually covered AHU filters in great detail previously, links in the video description below, do check that video out. The next thing we'll find are the cooling and heating coils. These are there to cool or heat the air. The air temperature of the supply air is measured as it leaves the AHU. This needs to be at a designed temperature to keep the people inside the building comfortable. This design temperature is called the set point. If the air temperature is below this value, the heating coil will add heat to increase the air temperature and bring it up to set point. If the air is too hot, then the cooling coil will remove heat to lower the air temperature and also reach the set point. The coils are heat exchangers. Inside the coil is a hot or cold fluid, usually something like a heated or chilled water, refrigerant, or perhaps steam. Now, we've discussed these in great detail previously in other videos. Do check those videos out, links are in the video description below. Next, we'll have a fan. This is going to pull air in from outside and then through the dampers, the filters, the coils, and then push this out through the ductwork and around the building. Centrifugal fans are very common in old and existing AHUs, but EC fans are now being installed and also retrofitted for increased energy efficiency. Across the fan, we'll also have a pressure sensor. This will sense if the fan is running. If it is running, then it will create a pressure difference. And we can use this to detect a failure in the equipment and warn the engineers of a problem. We'll also likely have a duct pressure sensor shortly after the fan. This will read the static pressure, and in some AHUs, the speed of the fan is controlled as a result of the pressure in the duct. So we'll also very often find a variable speed drive connected to the fan for variable volume systems. We've covered VAV systems separately, again, links down below for that. Then we have the ductwork, which sends the air around the building to the designated areas. We'll also have some ductwork coming back, which is bringing all the used air from the building back to a separate part of the AHU. This return AHU is usually located near the supply, but it doesn't have to be, it can be located elsewhere in the building. The return AHU in its simplest form has just a fan and a damper inside. The fan is pulling air in from around the building and then pushing it all the way out of the building into the atmosphere. The damper is located at the exit of the AHU housing and will close when the AHU turns off. That's a very simple and typical AHU, so what else might we find? If you're in a cold part of the world where air temperatures reach freezing point or close to it, then we'll find a preheater in the inlet of the fresh air intake. This is usually an electrical heater. When the outside air gets to around 6 degrees Celsius or 42.8 degrees Fahrenheit, the heater will turn on and heat up the air to protect the components inside from frost. Otherwise, this could freeze the heating and cooling coils inside and burst them. What about humidity control? Some buildings need to control the humidity of the air they supply into the building. We'll find a humidity sensor at the outlet of the supply AHU to measure the moisture in the air supply. This will also have a set point for how much moisture should be in the air by design. If the air's moisture content is below this value, then we need to introduce moisture into the air using a humidifier. This is usually one of the last things in the AHU. This device will usually either add steam or spray a water mist into the air. Many standard office type buildings in Northern Europe and Northern America have turned off their humidity units or uninstalled them to save energy, although they are still crucial for places like document stores and computer rooms. If the air is too humid, then this can be reduced through the cooling coil. As the air hits the cooling coil, the cold surface will cause the moisture within the air to condense and flow away. You'll find a drain pan under the cooling coil to catch the water and drain this away. The cooling coil can be used to further reduce the moisture content by removing more heat, but of course this will decrease the air temperature below the supply set point. If this occurs, then the heating coil can be turned on to bring the temperature back up. This will work, although it is very energy intensive. Energy recovery. If the supply and extract AHUs are located in different areas, then a common way to recover some of the thermal energy is to use a runaround coil. This uses a coil in both AHUs and a pump circulates water between the two. This will pick up waste heat from the extract AHU and add this to the supply AHU. This will reduce the heating demand on the heating coil when the outside air temperature is below the supply set point temperature and the return air temperature is higher than the set point. The heat would otherwise be wasted as it is simply rejected to atmosphere. As the pump will consume electricity, it is only cost effective to turn on if the energy saved is more than the pump will consume. Another very common version we'll come across is to have a duct sit between the exhaust and the fresh air intake. This allows some of the exhaust air to be recirculated back into the fresh air intake to offset the heating and cooling demand. An additional damper sits within the connecting duct to control how much air can be recirculated. This is safe and healthy to do so, but you will need to ensure that the exhaust air has a low CO2 count, so we need some CO2 sensors to monitor that. If the CO2 level is too high, then the air can't be reused. The mixing damper will close and all the return air will be rejected from the building. When in recirculation mode, the main inlet and outlet dampers will not fully close in this setup because we will still need a minimum amount of fresh air to enter the building. We can use this in the winter if the return air is warmer than the outside air, and we can also use this in the summer if the return air is cooler than the outside air, respective to the supply set point temperature. We'll also need some temperature sensors at the intake, return, and just after the mixing region. Some buildings require 100% fresh air, so this strategy can't be used everywhere. Local laws and regulations will dictate this. Another variation we might come across is the heat wheel. This is very common in newer compact AHUs. This uses a large rotating wheel. Half of it sits within the exhaust airstream and half of it sits within the fresh air intake. The wheel will rotate, driven by a small induction motor. As it rotates, it picks up unwanted heat from the exhaust stream and absorbs this into the wheel's material. The wheel then rotates into the fresh air intake stream. This air is at a lower temperature than the exhaust stream, so the heat will transfer from the wheel and into the fresh air stream, which obviously heats the incoming airstream up and thus reduces the demand on the heating coil. This is very effective, but some air will leak from the exhaust into the fresh air stream, so this cannot be used in all buildings. Another version we might come across is the air plate heat exchanger. This uses thin sheets of metal to separate the two streams of air so that they do not come into direct contact or mix at all. The temperature difference between the two air streams will cause heat to transfer over from the hot exhaust stream through the metal walls of the heat exchanger and into the cold intake stream. The two air streams need to cross over for this to occur, so it can be a little confusing to look at. Just remember the air streams are not mixing. Just before we wrap up, I just want to remind you to sign up for your free Danfoss Learning profile. Doing so gets you access to hundreds of engineering-focused e-lessons, including several about heat exchangers. It also enables you to earn certifications. So what are you waiting for? Go give it a try now. Links are in the video description below. The answer to the question I asked at the beginning of the video for what is the difference between an AHU and an FAHU is simply that FAHU stands for Fresh Air Handling Unit, meaning it is an air handling unit or an AHU, except it can only handle 100% fresh outside air. It does not recirculate any return air back into the supply stream. An AHU, on the other hand, can recirculate some of its return air into the supply stream. The building application and local regulations will dictate when and if this strategy can be used in a building. Okay guys, that's it for this video. Thank you very much for watching. I hope you've enjoyed this and it has helped you. If so, please don't forget to like, subscribe and share, and also leave your questions in the comments section below. Don't forget to follow us on Facebook, Instagram, Twitter, and obviously theengineeringmindset.com. Once again, thanks for watching.